Okay, I'm
We
going to have to
tested
hit it.
this. Nothing's changed.
Nothing has changed. Yeah, I'm just not able to advance the. Okay, here we go. All right. So the Webb telescope, it was designed to detect infrared radiation. I want to go back one more. It was designed to detect infrared light as opposed to visible light, which is what we're familiar with the Hubble telescope. So it could look at things that we've been unable to see with for example, the Hubble. It has three major missions. It's nominally 10 to 20 years. The thinking is it might actually make it to 20 years because they use so little fuel during the launch, but it's to observe formation of stars and the evolution of galaxies, search for the first galaxies that formed in the universe, looking way back in time, and measure planetary systems and search for potential life. So here's some pictures of the Webb during its development. On the left, you can see the actual telescope in a semi-unfolded mode. On the right, you see it in the lab with this huge infrared blocking screen to keep the sun's radiation from hitting the telescope. A little more detail of what the whole spacecraft looks like. On the left, you can see that on the very top, there's the telescope itself, and underneath is the transmitter back to Earth, and the science module that has all the cameras and everything just right behind the telescope. On the right, you can see the telescope itself. It's 6 meters in diameter with 18 hexagonal screens. They're actually coated with gold. It's not glass. It's a gold because that reflects infrared better. And then it's a reflecting type telescope in that the light from the big 6 meter panel is reflected up into a secondary mirror, and then reflected in through a hole back through the center of the telescope into where the instruments, the cameras, et cetera. This is almost exactly like my own telescopes that I have here, except on a much larger scale, and this one's 1 million miles away. I have a little video here, which there's someone, I'm going to admit this person. There's a little video here that shows some of the highlights of the launch and the preparation and launch. So this was a 30-year effort to build this telescope, and here you're seeing the final stages of it. You get a sense for the scale of it here. And then the shroud that's put over it for the launch. And then the separation. Goodbye. No human will ever see this again. It's gone, 1 million miles away. One thing you folks may not realize, this was launched by the Ariane and near the equator, and it gets a boost. There's a reason for it being on the equator because of the spin of the Earth. The actual rocket gets a boost from that motion. So that's an interesting little tidbit there. Okay, so a little bit more about the telescope itself. on the left, you see a comparison between the Hubble and the Webb. Now, the Hubble was goes way back, was launched in April of 1990. It's still working. It's had a few little problems, but they've managed to keep it working, and it might work for some time yet. The Webb is, you can see by, if you look on the right side, you can see that it has a much larger mirror. It's 6 meters in diameter. That's almost, over 20 feet compared to the Hubble, which is about 2 meters in size. And the other major difference, in addition to the fact that it's much bigger in diameter, it means it has about somewhere around 8 to 9 times the light gathering capability of the Hubble because of its the size of the mirror. But the other major difference, the huge major difference, is that the Hubble is focused on mainly visible light, whereas the Webb is focused mainly on infrared, going out to 28 micron infrared light. So those are the main differences. This is a little bit more detail showing this incredibly large screen that's blocking the light or the heat from the sun. This is an infrared telescope. It's designed to pick up infrared light. Unfortunately, the heat from the sun is in the infrared too. So this thing keeps the temperature on the right side of this, the sun side, it's at 185 degrees Fahrenheit. On the left side, it's minus 388 degrees Fahrenheit, almost 500-degree difference in temperature because of this heat shield. And it's about the size of a tennis court, so it's huge. This shows some of the instruments. There's 4 major instruments on the Webb. There's 2 spectroscopy spectroscopes, one for a very large field of view and others much more pinpointed. Then there's 2 camera systems. One is called the MIRI, which is the mid-range. Now I'll talk a little bit more about that, and the NIRCam, which is the near infrared camera. This shows some of this is the instrument panel here on the left of the screen, and you can see that it's quite large and obviously heavy. The one that the technician is working on is the NIRCam, and there's on the right side of the screen you see a diagram just showing the various pieces of it. So basically what happens is light comes in through the telescope, through the hole in the mirror, reflects off a pick-off mirror, reflects off another mirror, and then is split into 2 paths. The longer wavelength end, which is about 5 micron radiation light, and the shorter wavelengths go to 2 different directions. The cameras are basically black and white, but there are these filters. Each camera has its own filter wheel. Altogether, I think there's something almost like 20 different filters that allow light of different wavelengths to get into the cameras. Very complex system. And what's amazing is that the whole thing worked perfectly. The launch was perfect. The deployment was perfect. The focusing was perfect. The instruments have worked flawlessly. This is the journey that the Webb took to get to its what's called the Lagrange point. I'll show you where that is in a second. But in the 2-week journey where it traveled 1 million miles, it was gradually deploying on the way. And so when it arrived there, it was pretty well completely opened up. Where the Webb, this is a diagram that shows the 4 Lagrange points, actually 5 Lagrange points. The Webb is on what's called Lagrange point 2, which is in line with the sun and the moon, as is shown in the diagram. So what is the mission? Well, it's there's 5 different little cartoons here. One is what's happening in the early universe with the infrared light, infrared capability. It can detect things happening very much earlier in the universe than we've ever been able to see before. Understanding what goes on in how galaxies and black holes form, understanding the life cycle of stars, understanding planetary systems, including our own, and then finally actually investigating exoplanets. And this was, when this was first envisioned exoplanets weren't on anyone's screen. But in fact, the infrared capability that in the spectroscopy it has allows it, you'll see examples of that as we go through this. Okay, so we're going to show some pictures of some of the objects that the Webb has imaged. I want to just explain what these are. One big class of objects are nebulas, and nebulas are clouds of gas and dust. And mainly hydrogen, because hydrogen is the dominant element in the universe, but helium, oxygen, and lots of other stuff. All stars, including the sun, was formed in nebulas, in a nebula, a cloud of gas and dust. And basically what happens is some event causes a cloud to crunch, and once it's going, gravity takes over. And if it can somehow get to 10 million degrees Kelvin, a star is formed. What happens then is hydrogen starts a nuclear reaction that turns itself into helium. It transforms the hydrogen into helium with the helium has a little less mass than the hydrogen had, and that little less mass turns out to is energy, E equals mc squared, and that delta mass, and that gives us where all the light comes from. Okay, so so we're now going to see, and this is a nebula of object that I actually took here in Jackson Hole with my 6-inch telescope, my smallest telescope. But this is a cloud of gas and dust. This is what's called a false color image, meaning that the light, the image here, the colors in this image come from different elements. For example, the green in this is hydrogen, the red comes from sulfur, and the oxygen, and the blue is oxygen. And what this is called an emission nebula for that reason. So what happens is the light in the nearby stars excites the atomic elements, and they then re-emit light at a characteristic wavelength according to their atomic structure. And this image captures the light from just those 3 elements and nothing else. So you're going to see, we'll show you some pictures of Webb versions of these objects. Then the other thing we're going to look at are galaxies. And the first stars, one of the big goals of Webb was, when were the first stars formed? When were the first galaxies formed? Well, first stars, once the universe cooled down enough so that that the elements actually formed, they weren't ionized, they were real elements. And about 300 million years after the Big Bang, the first stars were formed. And then these stars usually were not just formed one at a time. They were often formed in these clouds, as I mentioned. And these clouds then sometimes form, or quite often form, into congregations of lots and lots of stars, billions and potentially, and these are called galaxies, which are collections of large number of stars. Now that you'll see here, the Webb actually identified the first galaxies that have formed were only 180 million years after the Big Bang, which was a major surprise. It was, no one had envisioned that they were that there would be so many stars formed that early. This is a picture of a galaxy that I took here in Jackson Hole with my, again, 6-inch telescope. Why do I have these larger ones? But it turns out the 6-inch is useful for very large objects in the sky. And this is the Andromeda galaxy, and it's the largest nearest neighbor galaxy we have. It's about 25 million light years away. And that's close, by the way, when you think about the scale of the billions of light years associated with the universe's scale. This galaxy and the Milky Way in about 4 billion years are going to emerge. And so it'll be an exciting time here in Jackson. Okay, so we're going to talk now about imaging with the Webb. So I'm going to just describe how most of the images you're going to see here are ones I did. And how did I do it? There's data that's on a website called the MAST website. You can get the data, but what the data comes out as are basically black and white images taken from the cameras. They're all, and there are a bunch of these images. Each one is goes through a different filter, so it's looking at light at a different wavelength. And then to make an actual images, the light in these images, I'll show you an example of one, is kind of squished, and they need to be stretched, and I'll show you what that means. And then we assign colors to them. Since all of the light from the Webb is you can't see with your naked eye, it's all in the infrared. We assign colors to the different wavelengths and create a false color image. And then there, as I said, then you combine these false color images to make a color image. And this is exactly the process that I use on my own telescope. I'm getting these images, these black and white images through various filters. I put them together and make color images out of them. Okay, so here is one of the early images. This is a single image through one filter. This is a 4-micron infrared filter. And the image on the left is exactly what it looks like when you get it. Then what I had to do was stretch it. And that's what the image on the right is a nonlinear process. So you try to bring up the brightness of the dim areas without increasing the brightness of the bright areas. So you see a lot more of the focal, the overall range of light in the image in the rightmost picture. So that's the first step. I'm going to see if I can get rid of this thing one more time. It doesn't seem to like to disappear, does it? Okay, so all right, stop that. Now it's not letting me. Okay. Okay, so this is the image that I made from, this is something called the Southern Ring Nebula. It's an object that we can't see in the Northern Hemisphere. It's in the Southern Hemisphere. It's a particular type of nebula. I'll describe that in a second. First thing I'll just tell you is how it was made. It was, I showed you the raw image at the 4-micron wavelength. There's additional, there's two other wavelengths, two other pictures that came into this. One was at 3.56 microns and another one. And so I assigned the colors. The longest wavelength, the 4, was assigned to red because red is the longer wavelength, green in the intermediate, and blue in the 0.9 micron wavelength. And then I assembled it into this color image, what you can see here. Now, what is this thing? This is a planetary nebula. And what that means is a star like the sun will eventually burn through all of its hydrogen. All the hydrogen will eventually get converted into helium. Once that happens, the helium will get squeezed because now, without the heat from the nuclear reaction, gravity really takes over, scrunches the helium, and it will start another nuclear reaction, converting the helium into carbon. However, once all the helium is gone, it'll crunch the carbon, but the star isn't big enough. The sun and this star, the origin of this wasn't either, and the nuclear reactions and the matter in the sun just sort of drifts away in various shapes, and that's what you're seeing here. This is a planetary nebula, it was called, and each of these, you can see the different, they're rings, and each ring represents a different phase of the star's evolution in this planetary nebula phase. This is a picture that shows the Hubble image of the same object on the left and the Webb image on the right. Now, don't get the idea that every Hubble image is not as nice as every JWST image. You'll see something where, frankly, the Hubble image is much more beautiful. But in this case, there's no question that the Webb is able to see detail that the Hubble just can't. Now I'll show you the next picture is it's the same picture I just showed you, but another one of the same object, but this is with the MIRI telescope, the MIRI camera, which is the longer wavelength, going all the way up to 18 microns in this particular case. So this is the same object, but taken with a different camera. Now, what's interesting about this, one of the things that's interesting about it, is that there's a little more detail visible in the center area because the longer wavelengths allow the penetrate the dust better. But you'll notice there's two stars in the one on the right, and there's only one star on the left. The reddish star on the image on the right is actually the remnant of the dead star. It's not even visible in here. That bright star is another star that's in the field of view, but it's not actually in this nebula itself. So the Webb was able to actually see the what's called a white dwarf star that was the remnant of the original star. Okay, so moving on. This, by the way, is the NASA version of those two pictures. So this is my version. Now, I like mine better, but yeah, I'm a little bit of a showman, and so I tried to make them look prettier, frankly, but in some cases show more detail. Okay, so this is something called the cosmic cliffs, and this was the actual first thing. The first object you might have seen in the newspaper about the Webb was this thing, and this is another nebula in the southern sky in the Carina constellation, and there's three wavelengths involved with this too. There's different sets of wavelengths. You'll know they're not always the same, but 4 microns, 2 microns, and 1.87 microns. Again, signing red to the longest and blue to the shortest wavelength. And there's a lot more detail. Well, you'll see. I'll show you what this looks like in a visible light picture, but there's a lot more detail visible in this than typically would have been visible in a visible light, just because you're able to penetrate the cloud here much bigger. And some of these towers, you'll see these spikes, like the thing up on the upper left there is something like 7 light years in size, so it's quite big. When you, I haven't really given you a view of distance in space, but let me just give you a quick summary of it. A light year is about 6,000 billion miles, and that doesn't mean a lot to most people. But if you think about it this way, the Voyager spacecraft is traveling outside our solar system now at about 35,000 miles an hour. It's going to take 40,000 years to get to the nearest star other than the sun. 40,000 years, and that's about 4 light years away. So you can get an idea how big a light year is. It's huge. And Pluto is, I think, 6 light hours away. Sun is 8 minutes away. Okay, so yeah, this is an image that I did. This is an image that I made of this object, of the larger nebula that the cosmic cliffs was taken from. The very top, the image, if you look carefully, you'll see at the very top of this image that cliff where there's the blue, the center in the middle, and there it goes into the reddish yellowish area on the top. That's where that image was. That is the location of that previous image that the JWST took. The center hole of this is cleared out. Actually, you're looking at stars through the center of this, and what's happened is that the bright stars in the area of their solar wind push the gas out, and so you actually create, and that's quite common in a lot of the images that you'll see. This image was taken down in Chile. It's because it's in the southern hemisphere. Okay, here's another nebula. This is a part of what's called the Tarantula Nebula, and this one also is in the southern sky. It was done with the NIRCam camera, 3 wavelengths, again, red being at the longest. And you can see some of the incredible detail there. There's a star cluster in the center and in a hole. And this is a part of what's called the Tarantula Nebula, as I mentioned, which is the nebula itself is about 1,000 light years in size, and it's located in what's called the Large Magellanic Cloud, which is actually a satellite galaxy to the Milky Way. It's not a part of the Milky Way, but is gravitationally bound to the Milky Way. And it's about 180,000 light years away, which is a long way. And it's one of the areas that produce a tremendous amount of active star formation. And yeah, and this one, just like the other one I just was talking about, the center has been sort of pushed out by the solar wind from the nearby stars. Okay, so this is a picture of the whole Tarantula Nebula that I made also, and this was taken with a much smaller telescope down in Chile, and the arrow is showing, you can see where that particular part of the nebula that was imaged by the JWST was located. The larger image is about 2 full moons in size, and this is huge. An example of this is if the Tarantula Nebula were at the same distance from us as the Orion Nebula, which is out there right now, not tonight with the clouds. In fact, I'd like to see some clear nights again sometime. But if it was the same distance as the Orion Nebula, it would take up half the sky. So you see this monster cloud taking up half your sky. So, but anyway, it's being 180,000 light years away. It's still quite large overall. Okay, here's another nebula, which is a favorite of mine because I spent a lot of my own time working on it. This is something called the Eagle Nebula, or a part of the Eagle Nebula. It's about 7,000 light years away, and it's visible in the southwest in the summer sky. This region of the nebula is called the Pillars of Creation, and that was made famous by the Hubble image in the 90s. And so the image on the right, the inset, is the Hubble image that was taken in about 1994. The image on the left is my image that I took right here in Jackson. So now you can look and you'll see that the Hubble image is sharper than my image, but there isn't many details that are visible in the Hubble that you can't also see in my image. So, but it's almost all, it's all there. It's just not quite as crisp. My image, however, took about 65 hours to make. A lot of imaging. I had to just get a really super good image that had high signal to noise, so I could sharpen it sufficiently to bring out the details. And these clouds, these pillars are clouds of gas and dust in areas where stars are forming. In fact, Hubble imaged this twice, once in the 90s and once, I think, around 2012. And there were small differences that were visible in the Hubble, the 2 Hubble images. Now, okay, so what do we have here? Well, we have the Webb version of the pillars on the left, and the Hubble blown up on the right. And you can see it's just a tremendous difference between these images. The most obvious difference is that a lot of what the detail in the Hubble is obscured because it's dust and the light can't get through the dust. Whereas in the this is a NIRCam again in the 1 to 4 micron wavelength range, and you can see a tremendous amount of detail in those pillars. But also look at this group of stars down here in the lower right. They're not even visible in the Hubble image. That group of 4 bright orange, yellow stars, they're not even there. A lot of the stars, you can see some stars definitely are visible, but look at the number of stars you're seeing here and how few you can see relative over there. And it's just in the nebula itself. And the reason is they're just being obscured by the dust. And so these are the 3. This actually was 5 filters worth. I pointed that out. Yeah, there was 5 separate filters that contribute to this image. So there's the red was from there was a filter that came in the 4.4 micron, which seems to be the longest wavelength of that particular NIRCam. Orange was contributed by 3.3, green 2 micron, cyan at 1.8, 7, and blue at 0.9 microns. So, and this next image is just a blow up, just allowing you to see even further the amazing detail in this. This to me is the most spectacular of all the Webb images that I've seen, is this one right here. Oh, and I meant to bring, I have a beautiful version of this out in my car. I meant to bring it in. Oh, well, forgot. Okay, now we're going to switch to, we're going to talk about galaxies. So this is an image that I made of a galaxy. It's Messier 74, and it's 32 million. And Messier was a astronomer who was trying to catalog comets, and he ended up creating this catalog of these other objects, of which there's 110 of them. Well, anyway, this is his number 74. And this is 32 million light years away. So again, what that means is the light from this left that galaxy 32 million years ago, and that we are photographing. So this is one done by Hubble. I took the raw data and made this particular image myself, but it's a Hubble-based image. And you can see a lot of the beautiful blue clusters of stars. By the way, most of the individual stars you can see in this image are all in the Milky Way, in between us and this particular object. This is also a true color image. These colors represent the actual colors of the object. It's not a false color image like all the Webb ones are. So here is the Webb version of that. It doesn't look much like the previous one, does it? The filter, and this one is taken by the MIRI camera, not the NIRCam. So the red in this is 21 micron wavelength, green is 11, and blue is 7.7. If I go to the next one, I superimpose the two, and so you can see these in this case, I've made it red so it stands out, but you can see the clouds, this web that's on top of the Hubble image that is totally invisible in the Hubble image. And the reason is particularly that mid-range camera is able to see light that is blocked to visible light. These reddish chains of this purple color comes from what's called polycyclic aromatic hydrocarbons. Anyway, that's what's actually emitting the light. What's going on is the stars are exciting these compounds, and then they're relaxing and re-emitting the light in this particular wavelength. So this is Messier 74 that I took here in Jackson. So this is my own image of it. It's not nearly as beautiful as the ones you've been looking at, but yeah, anyway, it was taken right here just to show you some of this one is visible in the northern hemisphere. Okay, here's another one, a very spectacular Hubble image. Let's see if I can. I think every time I use my pointer, this thing comes back, no matter what I do. But anyway, this is an image that's again in the southern hemisphere, but it's a barred spiral galaxy, and it's barred because of the center region has a long straight area, and that's it's called a bar. So this is known as a barred spiral galaxy. So this is an image that I made from the Hubble archive, which is available to anyone online. Yeah, and okay, and this is the JWST. This is also the MIRI version of this, and so I noticed that for the galaxies, they've chosen to use the longer wavelength camera more than the NIRCam. NIRCam camera seems to be used mostly in the nebulas. And so you can see the wavelengths range from 11 microns to 7.7. Yeah, and this web is actually showing areas, these bright areas are areas where there are star formation, but that whole web was invisible in the Hubble image. And then I've superimposed them like I did in the previous case on top, so you can see the two together. And this was always a little tricky too, aligning the two so that they were precisely aligned because the scale is different too. They're not photographed at the same scale, so nothing lines up naturally. And then the Hubble version is up in the upper right. And I'll end this sequence with the Hubble again. To me, I said, don't think all the Hubble image. I think the Hubble image here is frankly much more beautiful than the JWST, just from a standpoint of beauty. But there's a lot more information, different information that that you see in the Webb version. But the galaxies are more beautiful, I think, in the natural light of the Hubble cameras. Okay, so here's one last galaxy I was going to show. This is a pretty weird one. It's called the Cartwheel Galaxy, and this one is quite a distance away. This one is 500 million light years away. So 500 million years. Think about that. That's about when the Cambrian explosion occurred, and so the light that left this galaxy was at the time when the first little bits of matter, living matter, were really exploding into life as we now know it. 500 million years ago is when the light from this reached the camera. The image on the upper right is the Hubble version. A lot more detail. Yeah, and this one is the only one of the galaxies that combines both the NIRCam and the MIRI data together in one image. And it's that the main effect of the main contribution of the MIRI is the spokes in the cartwheel. The spokes stand out. If I showed you what it looked like in just the NIRCam, you wouldn't see these spokes so clearly because they're buried further into the nebula. Okay, so we're changing gears again, and we're going to talk about some imaging that the JWST has done of Jupiter. So on the left is an image that I made from 3 different wavelengths of Jupiter, and the right is the Hubble image. And you'll see there's several things that are quite different here on these. One is you'll notice the red areas on the top and the bottom. So you're actually seeing an aurora that exists on. It's a permanent aurora on Jupiter. And it's caused by ionized radiation that's coming from the nearby moons. I think the Io, the nearby moon, is creating infrared not infrared, but charged particles. And the magnetic field, the very strong magnetic field of Jupiter, is ionizing, and is creating this light. The main difference in terms of, forget the color is obviously different because this is a false color image and the Hubble is not a false color image. But you'll notice the detail, particularly in the polar areas, there's a lot more detail because this was taken with a NIRCam and is able to probe a lot deeper into the clouds that are essentially make up the outer layer of Jupiter. Jupiter is a gas giant, so there's no solid part of Jupiter. Maybe even the core is not even solid. This is another Jupiter image this is not one of mine. This was a NASA image, but it shows some very interesting features. One is Jupiter actually has a ring, a very faint ring, but it doesn't show you. I've never seen it in any of the Hubble images, and you can see it here. And you can see the auroras. The actual image here is similar to mine. I think mine is actually sharper of the planet itself, but so I've just done different signal processing to bring out the details than the people who made this particular image of the planet. But I wasn't able to bring out the ring. These are other images that I've made from not from throw a curveball here. This is not the Hubble. This is not the JWST. It's the Juno satellite that is still around Jupiter. And this has the most detail ever seen on Jupiter, but it's because this camera is within 2,000 miles of the planet. So when it's at its closest, it varies its distance. And for the very first time, there are images of the southern pole of Jupiter, because this particular satellite is going over the poles and not just around, because you're mostly used to looking at Jupiter from the side view, like in the Hubble image I just showed you. But here you're seeing, full planet view from the southern latitudes, and then of course right over the South Pole. Okay, so now moving into what's called the JWS time machine. So one of the major, one of the major features that was designed into this because with its infrared capability was to look back further in time. So why does having an infrared camera help you look back further in time? And the reason is that the universe is expanding, and the faster the objects that are further away are moving away proportionately faster. In fact, Hubble figured this out, and so objects that are billions of light years away are really moving away. They're not moving at the speed of light. At some point they will be, but they aren't. But they're moving faster, and so the limit for Hubble, you can see, is if you follow the first arrow, goes back to about 1 billion years after the Big Bang, maybe a little less than that. But JWST can go almost all the way to the point where visible light was first seen, and that's because of its infrared capability. And I didn't quite finish the whole story of this. Okay, so the objects further away are moving away proportionally faster. That's called a Doppler shift. And what happens is the wavelength gets proportionally longer the faster the objects are moving. This is very much like sound does the same thing. So a railroad train whistle going by you changes the pitch as it gets further away. It gets lower and lower in pitch. That's what's happening to the light. The farther away the objects are, the longer the wavelength. And so the Hubble telescope doesn't have the capability to even see this, because it doesn't have can't see into the infrared as nearly as far as the webcam. So, all right, and I've already did all that. Okay, so, all right. Oh, there's one more thing. All right, I think we all covered all that. Okay, so this there's 2 pictures here flashing at you. The yellowish one here is done by the Hubble, and the brighter one here is done by the Webb, and they're superimposed, so the features pretty much line up. But this is of a cloud, a cluster of galaxies. They're about 4 billion light years away from us, but there's light in this object, in this image I'll show you, that goes back to 13.5 billion years ago. And but you can see the difference between what Hubble also took. I think, let's see, Hubble took 2 weeks to do its image of this. And this was very famous when it was first produced, because this showed the incredible amount of galaxies that exist in the universe. And Hubble's deep field was just so dramatic at the time. But the Webb is showing in 12 hours, it's getting, not only is it brighter, there's things that are in this image, the Webb image, that are not in the Hubble image at all. And the other interesting feature of this particular picture is the field of view of this is the field of view of a grain of sand held at arm's length from you. So this is a tiny, tiny, tiny speck of the sky. Okay, and and a part of that, and so this was the very first deep field that the Webb produced, and people jumped all over it. And this, for example, if I can see it, but you probably can't, but this, where the little circle is, shows a little speck of light. And then when magnified, it looks like what you see here. And this is a galaxy that has been identified as being formed 300 million years after the Big Bang. So it's one of the earliest. This is at the time, this was a record for the oldest galaxy that was visible. You'll see here, and this galaxy is about 1,600 light years in size and about 1 billion stars. And what was amazing is that what amazed this, astronomers who study this stuff is that there would be galaxies this large with this many stars so soon after the Big Bang. And some of the early press that followed this, when this was first shown, this was shown in July or August, people were claiming the Webb has shown that the Big Bang didn't occur. And they totally misrepresented what was actually happened. What the Webb showed was the earliest galaxies were earlier than thought to have been from past data. We didn't have the data, but they thought there wouldn't be galaxies of this size so early. That's what was new. It's not like the Big Bang didn't exist. It was just, in fact, the time, it has nothing to do with the time scale associated with the Big Bang at all. But it's just the galaxy formation is clearly earlier than it had ever been thought to exist in the previously. In fact, so here's a graph, the only graph in the entire talk, I think. These stars represent the findings from that one deep field image that the Webb did, and it shows, in this case, on the left-hand side, this is time since Big Bang, billions of years, and so the record now is 180 million years after the Big Bang is the earliest galaxy that Webb has seen. But you remember the one I just showed you was 300, that was up here. Then maybe this one. And they kept on breaking records within weeks of time after this data was first shown, a new record was produced in terms of the earliest galaxy known. And so this is pretty remarkable. Also, the other fields, this is the look back time. In other words, how many years earlier from now. And you can see this one is almost 13.7 billion years. This graph is, this axis is interesting too. This is distance in terms of light years. And look at this, it says 35 billion light years. How can that be? The universe is only 13. What it means is that this object, which was 13 billion years when the light was emitted, is now 35 billion years away because the universe has expanded in the meantime. It's moved further away. So that's what this graph is. And the redshift it relates to how much the color of the image was changed due to the speed that is moving away from us. Yeah, and so as I mentioned, these records were broken within weeks of each other. This picture on the lower right is another one of these galaxies. This one was this 235 million light year old galaxy. Okay, this is almost done here. I just want to bring up a concept of something called dark matter. 90% of the matter, we have this stuff here that we're all made of. 90% of the matter is not this. It's something that is referred to as dark matter. And it was first noticed that something is there from galaxy pictures like this. So if you look on the left hand image here, look at the speed of rotation of the outer bands. And then compare it to the one over here. This is the actual reality over here, for example. And what scientists said, it can't rotate that fast because there's not enough matter. Kepler's laws will tell you the speed of rotation is related to the total mass of matter inside the rotation. And there isn't enough visible matter to explain a speed of rotation that fast. So something else was there. And it turns out that something else is actually 9 times more than the visible matter that we have, that we can see. This is matter that exists and it has a gravitational effect, but it's invisible. It can't be seen. It doesn't interact with light at all. Okay, so I'm just introducing the idea. There's a lot of dark matter around, but you can't see it. So how do we know it's even there? Well, one way we know it is by studying the rotation of galaxies. But this is a paper that just came out in December, just last month, about from the same deep field image that I've been showing you all along here. And what they've done is in this upper left graph, they've taken 3 of the wavelengths and averaged them, the light. They've added the light together and just averaged them. And from that, they were able to see a great deal of detail in how the light changed, the darkness to brightness, it was changed. And it represents plumes, motion of stars, clouds of stars moving in the direction between the dark areas, between the light areas and the dark areas, these various plumes, as it's called in the graph here. And the thinking is that these plumes are actually following paths of dark matter, that they're responding. The area in between these clusters are devoid of stars, and this is very dim light. They've been able to brighten it up. And by following by looking at this and looking at it in detail, they are seeing the pattern of brightness. And in other words, the density of stars are actually following the density of what they've modeled for dark matter. So this may be a way of actually seeing the evidence of dark matter directly without being able to actually see it see it through the existence of these star maps, whereas you can't see it with optical methods directly because it's invisible. Okay, so yeah, and this light is they point out that this light is dimmer than 1%. It's 1%, less than 1% of the darkest part of the darkest night sky you can see here. So it's very dim light. Okay, and the last thing we're going to talk about is exoplanets. So this is a plot that shows one exoplanet taken through 4 different wavelengths of light. See if I can get rid of this thing here one more time. 4 different wavelengths. The one on the left is 3 microns, 4.4. Then it jumps into the Miri range, 11 microns. And the star that's showing up here is where the actual star is, but it's blocked out. And one of the instruments, one of the features of the Webb is that they have a screen, a way of blocking the light from the star so you can see the planet. So these are the very first direct images of an exoplanet. Very first. And you can see the different how they appear in different wavelengths. But that's amazing, you know, that and in addition to okay, and since I did that, I have to do this okay. So yeah, and as I said, it's the first direct oh yeah, the planet here is about 6 to 10 times the size of Jupiter, and is much younger, 15 million years old, and it's actually much further away from the star than Jupiter is, 20 times the distance from that star compared to Jupiter's distance from the sun. Okay, and this is another example of what Webb can do with its spectroscopy. So it's what we have here is you probably may not be able to read it, but it says wavelength of light on the bottom axis and amount of light blocked on the upper axis. And it's showing you different absorption of water. It's identified these peaks and valleys as areas where there's water. And so we're able to determine that in the atmosphere of this particular, or in this planet, there is definitely water. And they can also detect not just water, but other elements, carbon monoxide, various other anthropological elements as well. And I think that's the end of the talk. So this is it, and I show you this one because this is my favorite of all the images that I made of the Webb. It's spectacular. All these, it's cut off here, but all these images can be seen if you're interested at my website, earthandskyimaging.com, earthandskyimaging.com. I even have business cards if you want one. So that's it.
Well, thank you, Mike. Can you hear me?
Yes, we can.
Fantastic. Well, that was quite the presentation.
Thank you.
We had 57 people on Zoom, by the way, so we have quite the crowd. That's
I sent
still
this.
There.
I have a lot of my friends on this call because I sent out a notice to 300 of my closest friends. And you can see quite a large number of them managed to join me tonight. So I appreciate that. See ya. Hi, Chuck. I see him here.
I do have a couple of questions, Mike. But do you have some from the audience
let's have
there?
questions here from the,
Okay.
yeah.
And you'll need to repeat the questions, Mike, for the Zoom
I will.
audience.
The question is, how did they gauge the age of that exoplanet? And that's a good question, and I don't have a good answer. Sometimes it has to do, I'm just going to guess a little bit. Sometimes it has to do with what the area around it, because when a planet is very young and it's just formed, there's still debris around the planets, and that gives them some indication of how young the overall solar system is. Like our solar system was chaos in the first, 100 million years. It was just, and it got sorted out over the first billion years of existence. And so I think that's part of the story, but I'm sure there's more to it than that. Yeah.
Well, actually, Mike, I have a related question, which is, how do you determine the age of a galaxy?
Okay. It all has, what they're actually telling you is the age of the light that came from the galaxy. So, these early galaxies, the light was emitted, and these are the very first galaxies, 13.7 billion years ago. So the galaxy obviously probably, might have existed a little bit before that, but that's the age of the light from the first time we've been able to see it. So that's.
But how do you know that?
How do they know that? Because that by looking at the speed of the age. Well, okay, it all has to do with the redshift. It's all Hubble's relationship. So objects that are so far away have so much redshift because they're moving away. So it's all related to the Hubble curve, where Hubble figured out that the further an object away is, the more it's moving faster. So by measuring the actual redshift, you can determine how far away its speed and how far away it is on the Hubble curve. That's what Hubble did. And that's the answer to that question.
Okay.
Now, there are other ways in which closer galaxies are determined by measuring supernova. But these are so far away that you can't do it that way. But certain types of supernova, like the what's called the type 1A supernova, has an absolute brightness that's the same. And so by measuring the actual brightness, they know the absolute brightness, so they can infer the distance from the brightness of how the light falls off due to just 1/r². And so that's the way, but that only applies to things that are much closer than these. These things are so far away, so they're using the Hubble law to work it out based on measurement of the redshift.
Got it.
Yeah. Oh. Yeah. Yeah. Right. Yeah. Yeah. Exactly. Yeah. Sorry. Yeah. Yeah. You're right. Yeah.
Can you repeat the question, Mike?
Yeah. It was just pointed out that I was mixing the name of a person and the name of a telescope in various parts of the discussion. And this is true. The Webb is I think in every case I've used, it has to do with the telescope. But in the case of Hubble, it always was the telescope until this last discussion just 2 minutes ago, when I was referring to what Hubble did by working out the distance and speed redshift relationship. "18 hexagonal plates of, and it is not a glass. They're not a glass, and they're coated with gold." Yeah, the question is, are the individual 18 elements comprise the Webb mirror, such as it is? Are they articulate? And the absolute answer is absolutely. The very first image that they did when they first turned it on, they got 18 pictures of the same object. Yeah, they had to, and that's the other amazing thing. Not only did the launch go perfectly, they used less fuel in the launch, everything, but they are actually able to do this alignment, and you get the detail, like in that. Just look at the detail in these images. Yeah, so that's just astounding.
Mike,
Yeah.
I do have some chat questions.
Sure. Okay.
Okay, so one is, well, lots of online kudos. So thank you for that, for the talk from a lot of people. So does the JWST detect any wavelength within a range, or does it only detect discrete wavelengths?
Yeah, the answer, okay, everybody heard the question. Yes, some of those filters are much narrower than others. Some of those filters are nanometer wide wavelengths, and some are wideband. And I wasn't careful in telling you which one was which. But some of them, and for example, it's the same thing with my telescope. I have red, green, and blue broadband filters that cover the whole range of red light, green light, and those are broadband filters. Then I also have filters that allow only hydrogen, the wavelength associated with hydrogen emission at 656 nanometers. And it's only 3 nanometer wide window of that. So the answer is both. Some of them are broadband, wide range. Some of them are narrow range, and that's why they have. I think I meant to look at it in detail, but I'm pretty sure there's almost 20 different filters on those cameras.
Well, there's a related question then, which is a bit more basic, which is, can you give us a primer on how you use color filters, how you use the filters to produce the images? Okay, well, it's actually pretty straightforward. If you know anything about image processing or even Photoshop. So what you do, the first thing you do, and I was trying to show you that earlier on, but I went through it pretty quickly. You create these black and white images that you get through any given filter. So you have those, then you assign a color to them. And so I indicated the color choices that I made in doing this. And then you assemble a color image. So now you have a color image that is in red, a color image that's in green, a color image is in blue. In other cases, orange and cyan and other colors I added in. And all of those were then put together in Photoshop or some other software tool. So in Photoshop, there are ways to create a color image out of 3 separate black and white images associated with the various colors. But since these are all false colors, none of them represent real colors. But the Hubble galaxy pictures were real colors. Those are a red filter, a green filter, and a blue filter. Real in the sense that it's the same color you see with your own eyes. But in all the other cases, no, the colors are false color, but they were created out of individual black and white images, then with colors being assigned to them. You know, I mean, a regular camera has filter. It has three, this goes on in all photography, by the way. There's nothing unique about this in this respect. Yeah.
We have a different kind of question here. If you,
Okay, we got, let me take another one from the floor here.
Yep.
Yeah. Yeah. Oh. Yeah. It's difficult, but there are ways.
Mike, the question.
Okay, the question is, and when you look at the stars, that the image that I showed of the pillars of creation, there are stars all over the place. And so the question is, how do you know where the star is relative to the nebula itself? Is it in front of the nebula or is it in behind the nebula? So how do you know that? Well, it turns out, again, this is a lot of astronomy that's been done in the last 100 years. It turns out 90% of the stars in the sky are what are on a curve that that is a known curve, and the color of the star tells you its size and knowing and its brightness. And once you know its brightness, you can tell its distance. So that's one way to do it. So that's the quick answer to that question. Oh, absolutely not. No, yeah, absolutely not. And as I mentioned on the galaxy pictures, all the individual stars you saw in those galaxy pictures were all in our galaxy. There's no question about that. You cannot see a individual star, 20, well, with my telescope, you get, but people do see individual stars out hundreds of millions of light years with the right telescopes. But most, us amateurs certainly can't do that. And so you just measure the color, and you can, and then you're guessing that this is a main sequence star. It's what it's called. And if it's on the main sequence, you look it up, what color, and then from that you'll get brightness, and then you can determine distance. As that whole business of determining stellar distances was a major issue. There were major debates about this 100 years ago. 100 years ago, people were arguing as to whether these clouds that we now know are galaxies were nebula, that the Milky Way was the universe, and because they could measure distance. Now, one way to measure distance is something very close is parallax. You measure the distance, the angle to the star when you're on Earth from one season to the other. You measure the difference, and if it's close enough, you can actually see that. And now with modern instruments, they can use parallax to a lot further distance than but forever. The big breakthroughs was really Hubble noting that in the 20s, that these things like the Milky Way were not in our galaxy. They were millions of light years further away. And that was a big breakthrough in terms of being able to know. And scientists are still working this issue, trying to figure out measured distances. One of the main challenges of astronomy.
So Mike, for the Zoom audience here, let me just say that the recording of this talk will be available as a link on the Geologists of Jackson Hole website in a day or two following this talk. So just an FYI. And then there is a question, which is there what is the best website to go to see the Webb telescope images? Is it yours, perhaps?
Mine isn't bad, because frankly, I think I have all of them that are I've seen available. I haven't seen any. The latest one, which I did within the last month, is the one of the Pillars of Creation. I haven't seen another one since. And so earthandskyimaging.com, but you can just look up NASA JWST, and you'll see lots of different websites that'll show the various pictures. And if you're interested in the science, you can do the same thing, and because they will have links to the various scientific articles that have been written. And there's quite a few of them that have been written. All those revelations about how early these galaxies, how far back in time they went, were all related to papers that came out fairly quickly.
So can I ask another technical question from the chat? Do you have any estimate of how many photons were collected to make the image for that farthest galaxy?
Oh, gosh. I have no idea. But you can see it's dim. And yeah, we're still talking about a lot of photons, I'm sure, but that's an interesting question. But we're getting down to quantum physics here and ability to collect light over a reasonable amount of time, because the way in which, of course, you collect light for dim objects is you expose for longer and longer times. And so that's why I said it takes, for me, when my telescope, 60 hours to see some of these images. You can see just the difference between hours with the Webb and weeks with the Hubble, because that's the light gathering goes as the area of the mirror or the telescope. And when you have six meters versus 2, that's a ratio of 3. Square that's 9 times more light gathering. That means you're going to gather 9 times light that much faster. So that's why a big telescope is nice. You see things a lot sooner than you would otherwise see them. Yeah, exactly. Yeah. Oh, I'm sorry. Yeah. Okay. Sure. Yes. Yeah, the question was, has this work shed any light on the question of how galaxies form? Do they form from the inside out or the outside in? And you could see from my simple cartoon, it would suggest that they form from the outside in, that the stars gradually just coalesce because of gravity. But I don't know that I haven't read anything more illuminating than that. Yeah. Yeah. Any other questions from the audience? No, I think we're done here. So.
Okay, I have some more here. How do you determine the composition of distant objects, taking into account the redshift for a given wavelength? In other words, does the redshift make it harder to identify the original composition?
I would think that yes, the answer, I'm sure it is, because what they're doing is they're assuming because obviously something that was very red by itself will, and so you're looking at something. Yeah, I would think that that is a conflicting issue, and so that somehow has to be sorted out. I think at those distances, frankly, that's one of the corrections they have to make. In fact, now I remember this now, because the objects that are further away, like these, are going through a lot of dust, and the red light is going to get through that dust better than any other light. So corrections have to be made for that effect. That particularly because the light, the longer wavelength, the shorter wavelength light is going to get filtered out by the dust between this object and us. And so that's a factor that has to be allowed for, that changes that equation about redshift uniquely determining distance. Correct. And so there are correction curves that are used to deal with some of this stuff. But that's a good question.
So another question is, what is the next telescope that they are working on beyond the Webb, and what will its objectives be?
Well, I think one that you read about now and then is a gravitational telescope that will be a space-based telescope that will allow objects that are much larger to be imaged with gravity waves. The gravitational telescopes we have on are based on kilometer type of distances between where the motion is measured. And that doesn't work for really big objects. So what we've been able to detect now are mergers of relatively small black holes and on stars. whereas the space-based version of this will be, these things will be much further away. And seen, for example, what is a dream would be, there has to be gravitational waves produced by the Big Bang. But the wavelength of these are going to be horrendously long. And so it's going to take a detector that's huge, maybe the size of the universe. I don't know. But the bigger the object, the bigger to measure the wavelength of this, you have to have these your detectors that much further away. But that's one of the space-based telescopes that is being considered. Clearly, on the surface of the planet, there are all sorts of telescopes being built. There's the 30-meter telescope being built. Can you imagine a telescope that's 30 meters? We're talking about a Webb, which is 20 feet in diameter plus 30-meter telescopes. These are being built right now, and these telescopes will use what I call adaptive optics. One of the problems with a big telescope is atmospheric blurring, but they will have individual, the telescope will not be a single mirror, it'll be many mirrors, and the ability to actually use what's called Schlieren optics to adjust the individual segments of the telescope to cancel out the blurring of the atmosphere. So the big telescopes are being built right now on our planet are all based on this, using adaptive optics. That's one thing, and of course you're right. We want to put a 15-meter telescope on the top of Mauna Kea in Hawaii, and that's I guess that's going along, but it's been slow. Well, yeah, the question is, can you apply a synthetic aperture to something that large? And the answer is, I have no idea. I won't try to. Yeah. Anything else?
Well, Mike, I need to tell you something, which is that Dr. Stephen Centuria,
Oh, yes.
your PhD advisor from MIT, has been on the call.
Oh, wow. Okay. Thanks, Steve, if you're still there.
He is.
Yeah. Some of my classmates from MIT are online. They're councilmen, are good friends from they're there, and fraternity brothers. Yeah.
All right. Well, that's all the questions from chat.
Okay. All right. Well, I think we're done here too. So we'll wrap it up. We have, just for the record here, let me just count. 1, 2, 3. Has anyone made a count here?
Yeah.
23,
Bill Newcomb
23
did.
people. 23 people here. Yeah.
Thank you. Perfect.
Yeah, and 50 some on Zoom. So
yeah, we had a max of 58 on Zoom.
Yep. All right.
So very, very well attended. Thank you. Thank you again, Mike. And thanks from everybody on Zoom. We got lots of accolades here on chat.
Okay, great. Thank you.
Okay, I'm going to end the call for all.
All righty.
Take care.
Oh, glad.
Nelson.
Oh, yeah.